another bad chat with Art again.
Right. Sometimes people start signing up, connecting soon. Yeah. Okay. A few people. Yeah.
And you'll control our cameras and microphones, I guess, when it's time to add or remove us.
No, that's up to you.
Okay.
You're in charge. Yeah.
Okay.
Yeah. So it's yeah.
So Bob, it sounds like class is starting.
It's what?
People coming back to campus, or
so the graduate
on
students,
MIT, how it is going? Like,
graduate students and postdocs are back in the lab at a 50% level, like 25 hours a week. But everybody has to be very careful.
Oh, that's a limitation.
Wearing masks and
distancing
and so forth. So
okay.
And then in the fall, the seniors are going to come back to campus.
Okay.
A lot of them have senior thesis projects of various things.
Right. Yeah, it's similar here.
Yeah. So it's yeah, that's what's happening so far. And we're
here.
Go ahead.
We kind of having this second wave. It's coming. It's kind of big one. Second wave. It's coming right now this week. So we gotta be more careful this week and next week.
Yeah.
In Osaka.
Yeah. Well, yeah, that's happening. They're beginning to worry a lot about that in Massachusetts.
Yeah.
You know, a second wave. People are getting very nonchalant and casual about distancing and wearing masks.
Yeah.
Yeah, so we generally wait till about 3 or 4 or 5 minutes after the hour before we start.
Okay.
Yeah.
Oh, it turned off. It's live.
Well, you need to get up and move around probably to trigger the light motion detector.
I think there's a timer. I mean, since like, now it's like
it looks like it's just the midnight, right? Yeah, it's a timer.
Yeah. Okay. So a few more minutes. Yeah. So it's yeah, Moderna, this Cambridge-based company, is projecting that they're doing very well with the vaccine. So they started a 30,000 person trial yesterday or Monday.
Oh.
The 27th, yeah. 89 different locations in the U.S. So they have an mRNA-based vaccine. They put into a lipid nanoparticle and inject. Injection, 100 micrograms, and so everybody's hoping that will be a successful vaccine.
Yeah. How long it's gonna last? That's the problem. Right? That's the question.
Well, that's one of the questions. Yeah. There are lots of questions. Yeah. So.
Oh, good.
Yeah. So we just got our 0.7 probe the other day, and
wow.
And it
for DNP? For DNP?
No, unfortunately not for DNP.
Okay.
We ran it for about a week, 2 weeks, and it crashed. The rotor crashed. So
some
of one of the guys is on his way out to Brooker to pick it up this morning. It didn't destroy the coil.
Okay.
That's normally what happens.
Mm-hmm. Mm-hmm.
So, yeah. Okay, a few more minutes and then Kong can get started, right?
Yeah, sure. Sure.
Yeah. Okay, why don't you, let's go forward, Kong.
Right. Yep, sure. Let me try to do this. All right, so I think you all can see my screen. So greetings again. Welcome to our Zoom webinar that has been going on for I think we started in April. Now we are in end of July. So I think this is our 14th or 15th session. Thank you for staying with us all this time. I'm gonna say the same thing again. Subscribe to the mailing list because I will be making important announcement. I mean, one of the announcements will be made by Bob soon after I finish with this briefing. And then if you're interested in our previous recordings, some of the sessions were recorded and they were posted on our website. Oh, there's a mistake here. I mean, we changed our website, but this link will still work. And then if you have not been to our Zoom webinar before, if you want to ask questions, please use the Q&A function that you can see at the bottom of your Zoom interface, which you can, not only you can ask questions, you can also vote on it, and also you can comment or help to answer if you want. Otherwise, if your question is too long and if you think that asking the questions verbally would be easier for you, don't be shy and raise your hand, and then we will unmute you, then so that you can ask your questions verbally. And don't use a chat function to ask questions. You can use chat to say hi and whatever. And lastly, all the Q&A that were asked in the previous sessions, they were uploaded to the Dropbox, of which the link can be found on our group website. So don't bother taking a screenshot because I will copy this text and paste it in the chat room. And I will pass the session to Bob, of which he will make an announcement on the fate of our future Zoom webinar and also introduce our speakers today.
Okay, so the first thing I wanted to tell everyone about is that we're, as of September 1, I have to start teaching and many other people start teaching too. And a lot of classes, it turns out, are on Monday, Wednesday, Friday, often in the morning. So we've made the decision to move this Zoominar, this webinar presentation, to Tuesday at 11 a.m. All right, so instead of meeting on Wednesdays at 11, we will meet beginning in September on Tuesdays at 11 a.m. So that's one part of it. The second part of the announcement is that we will actually be combining our efforts with the educational DNP efforts that have been ongoing on, I guess, Friday mornings. So they're going to be also moving to Tuesday at 11 a.m. and they will alternate weeks with us. So one week we will have this particular Zoominar, and then the alternate week we will have the educational session. And again, that will start in September, approximately whatever the week of September 1 is. I think September 1 is actually a Tuesday, will be the first one. And then we will have the next one, I believe, on September 8th. Is that correct, Kong? Yeah.
I think, if I'm not mistaken, I think we will have our sessions on 4th and 18th. Okay, just stay tuned to the announcement. I will.
Yeah, stay tuned to the announcements. We will get everything out. It's a month away. We have 4 or 5 sessions left in this particular format before we do this change. But we wanted to let everyone know that in September there will be a change of time. There would be no change of time, but there will be a change of date from Wednesday to Tuesday. Okay, with that, we have 2 really excellent speakers today. Yoh Matsuki, who is a professor at Osaka University, at Protein Institute in Osaka, and he's going to be telling us about his low temperature DNP experiments, which he looks at the surface only. And the second speaker is David Bryce from University of Ottawa Chemistry Department. And David, of course, is a world authority on quadrupole NMR. So Yoh, you have the virtual floor. Thank you.
All right.
Yeah.
Okay. So you hear me, right?
Yeah.
Do you hear me? Okay. So I'd like to thank Con and Bob for this opportunity to speak today about our work. We're making methods and instruments for high fidelity DNP. So I want to talk about that. This is overview of our system. We have 700 magnet here. Where is the pointer? Here. So we have the spinning system as well as the gyrotrons as usual. But there are two unique features. One, that is the helium-based spinning system for ultra low temperature DNP, as well as this double gyrotron capabilities. But I'm not gonna tell you about gyrotron today. I wanna focus on closed cycle helium spinning system, and then move on to the method part where we quantify polarization distribution in space and do some kind of double domain selective spectroscopy with DNP. Now on to the spinning part, we are motivated by this decreasing efficiency of the cross effect DNP at high fields. This is the enhancement factor for Torapol and Yulia as a function of B naught. If you go up in the field strength, it's really coming down. And we typically have the enhancement in the order of 10 or so at, close to the 20 Tesla. It's too bad. So about more than 10 years ago, we really start looking into this ultra low temperature DNP, because at lower temperature, you get greater static polarization as well as the dynamic nuclear polarization. And on top, it's possible to have lower thermal noise level as well. So basically, you have a lot of benefits in one stone. And for that, of course, we need cooled helium gas for bearing and driving gas lines. So first, we started out building this liquid helium boiling off spinning system for ultra low temperature DNP. It took some time, but we suffered with this system from like unstable temperature and spinning, relatively high cost for doing measurement because we boiling off a lot of liquid helium. And also it lasted only less than 10 hours or so each time because we couldn't refill this pressurized helium dewar while doing the measurement. So it was a lot of fun, but it was kind of too experimental system. It's not for like routine DNP measurement for biological things, which needs long and stable measurement time. So it was around 2012. So we spent 2-3 more years kicking around this. We spent a lot of time and efforts on this, which has culminated into this very fast example of closed cycle helium spinning system. There's no liquid helium anymore, anywhere. Instead, we are compressing helium gas, which is sent out to, which is regulated and then cooled with the electric gas chillers on the fly and sent out to the probe for sample cooling and spinning. And the return gas is immediately recompressed and recirculated in this closed loop forever. And in this way, first of all, the temperature and MAS rate became pretty stable. And it is long-term stable. This is a plot for 2.5 days. And if you leave it it just stays there forever, like weeks of measurement is easy to do. You can do a lot of things at a time. And of course, the running cost is pretty low because we're not consuming any helium for sustaining MAS. Of course, you need to pay the electricity bill for the GM coolers, but it is only $2 to $9 an hour or so, depending on what temperature range you need. So it's pretty good. But notice this, we're paying a lot of money for electricity in Japan. It's very expensive, right? Still, this is making a factor of 50 or so lower running cost than boiling off a lot of liquid helium. So if you're paying less for the electricity, you get a lot more benefit out of this. So if you're interested in, just wanted to mention that this system is now commercially available from JOL. Now, what about the enhancement factor? As we expected, it steeply went up with dropping sample temperature and reaching 300 at 30 Kelvin at 16.4 Tesla. For the total sensitivity gain, including the Curie factor as well as the depolarization effect, it's reaching a factor of 1,000. It's kind of impressive number, right? It's like 10 times better than conventional 100 Kelvin DNP. That's good, but now beyond the sensitivity gain, we wondered what else could happen with this 1,000 times bigger polarization than bigger than normal, right, at high field condition. This is an interesting part because very high external order or Zeeman order will automatically produce some internal order, meaning that in this density operator, the spin correlated term will start to have a significant amplitude. And if you calculate it, actually it is only about a factor of 10 smaller than the lowest order Zeeman order term. Should be directly observable in experiment. So we did this simple experiment where basically we hyperpolarized proton and observed the carbon NMR with a 90-degree pulse. But if you do this 180 pulse on proton in the second experiment, this spin correlated term will be embedded in sign. And by just subtracting these two data sets, the spin correlated term will be selectively observed. That's an idea. And of course, by just adding these two data sets, the Zeeman order term will be selected. Right, this cross term for helium-nuclear two-spin system will look like dipolar split, antiphase, powder pattern, convoluted with the spinning side bands like this. And in experiment, we got this. This very good agreement indicates that already at 35 Kelvin, the high temperature approximation is visibly violated. And the spin correlated term is big enough and readily observable in experiment. Subsequently, we also noticed that by just taking this spin correlated term to the Zeeman order term, this will tell you, directly tells you about how many percentage of proton polarization you have in your sample. And we did that, we found the 7.4% at 30 Kelvin, which is pretty high, kind of too high, or at least a little higher than we expected in the beginning. But soon we realized that this experiment, it's not like evaluating polarization level average over whole sample or anything like that. Because this is what's happening. The build-up time tau, during the tau, the proton and carbon polarization is coming up in a very different time scale. For example, the proton T1 is just a matter of seconds and distributes like up to tens of nanometers or so around the radical molecule. On the other hand, the carbon T1 is usually much, much longer in the order of 3,000 sec at this temperature. So there is no SZ in this cartoon at this point. But the exception is the carbon, which is experiencing PRE from the electrons within 2 or 3 nanometers from the electrons. That comes up much faster in the order of half a minute or so, generating this spin correlated term to the space right next to the radical molecule. And then we actually used this spin correlated term to calculate 7.4%, meaning that this particular experiment, based on this direct polarization or DP based experiment, is primarily sensing the polarization level within nanospace around radical molecule. So we extended this experiment to CP-based experiment. What's happening now is the carbon is hyperpolarized first with CP, like this. And then we're going to measure the polarization level, proton polarization, as a function of tau2. With non-zero tau2, the proton polarization is coming up rapidly and diffuse, reporting the polarization level from the nearest to farthest end from the electron within meso and deep meso space over several seconds of tau2. And later on in tau2, the PRE now pulls the carbon polarization within nanospace back down to the thermal equilibrium level, kind of desensitizing IZ-SZ within nanospace, making this measurement even more reflective to the polarization level far away from the radical molecule. So with this model, this experimental tau2 dependence, which has this particular shape here, can be interpreted as right after proton T1 in several seconds in tau2, the polarization level within mesospace is observed. Then later on, after this slow decay due to the PRE, the deep mesospace polarization is observed. Together with the nanospace polarization measured with the DP-based experiment, you clearly see this very steep polarization gradient that's set up around the radical molecule. The sample was alanine in highly deuterated DNP juice. Now, what if we do the same thing on highly protonated sample? We did that, we found this very much flat polarization distribution, which is not surprising, right? Because this very strong spin diffusion supported by dense proton network is really pulling out the polarization farther away in space from the electrons, leading to this flatter polarization distribution. Maybe people kind of knew this is happening in mind, but this is experimental. We kind of able to directly measure the polarization distribution in space. So this has made us more and more interested in the inhomogeneous distribution of hyperpolarization in the sample system, which should be a function of the relay efficiency of the polarization in the system, which is dictated in turn by the local T1 for proton. Because proton T1 is most significantly affected by the methyl group rotation at low temperature. So I dig into the literature, found this interesting correlation between the reported enhancement factor and the number of methyl groups or methyl group density in each sample system. Without methyl group here, like urea and proline, including hammerhead ribozyme sample, the enhancement is pretty high. But if you go to the regular proteins, even membrane proteins, which tends to be high in methyl group density, it is really coming down, especially at high field conditions. The effect is even stark with small molecule crystalline samples. If it is methyl loaded, the enhancement is very, very low because of this very dense molecular packing in the crystal. So this must be one of the reasons why we always see much smaller enhancement factor in real applications than urea or proline, meaning that those protein samples a lot of times diffusion limited in DNP. A prominent example will be this microcrystalline MLF. MLF is very popular, widely used standard sample in solid state NMR, but I've never seen any enhancement data for a long time. And actually in my hand at 16.4 Tesla, there was absolutely no enhancement at all at 100 Kelvin. This is microwave on, shown in red, and off is blue. No enhancement. The situation must be a lot better at ultra low temperature because the methyl group rotation will be largely suppressed at those temperatures. And actually, as we found with this MLF sample, there's almost no heteronuclear NOE observed at around 30 Kelvin or less, meaning that there we should be able to optimize the polarization relay in this strongly diffusion limited system like crystalline MLF. So here you go, the enhancement factor for MLF, it's really picking up with dropping sample temperature, reaching a factor of 15 or so at 30 Kelvin. The build-up time constant was around 20 sec at 30 Kelvin. So in general, 30 Kelvin DNP polarizes these real sample, like methyl-loaded sample, much better than conventional 100 Kelvin DNP. Well, the enhancement of 15 sounds not too impressive, you might say, but you have to remember that within this 20 sec or so build-up time, the polarization is only allowed to sink into the crystal by 130, 140 nanometers or so from the crystalline surface, leaving largely the crystal core at the thermal equilibrium state. This has given us the factor of 15 overall, and based on the average crystalline size of about 5 microns, you can calculate this back, like what was the surface enhancement, and we got this factor of 90 or so. So it means that the crystal surface is supposed to be highly polarized without any problem. I said it's supposed to be, but remember we can measure it directly, using this spin correlated terms like we do in a couple of minutes ago for alanine sample. But in this case, MLF has a number of carbon resonances. We had to modify the original one to 2D version to resolve this in-phase, anti-phase term into this indirect dimension. And this gave us an experimental surface polarization of 3.1%, which is corresponding to the enhancement of 80-something, which is within a very good agreement with the previous estimate based on the spherical crystalline MLF. So now we are getting more and more confident about this crystal surface, which is highly polarized. Then we thought maybe we can find some use of it. We can probably selectively observe the crystalline surface. In contrast to the surface-enhanced DNP, which is intrinsically contaminated by the signals from the crystal core, which is only thermally polarized, but highly abundant in the sample, producing very annoying background signals in many applications. Instead, we could probably excite multiple quantum coherences selective to the crystal surface, only using one single 90-degree pulse, right? And removing all the thermal polarization from the observation. For example, if you select the DQC with this 90-degree pulse and phase cycle and reconverging it with the recoupled double quantum Hamiltonian, this will be a two-dimensional DQSQ spectroscopy, but surface-only DQSQ spectroscopy, free from the background from the crystal core, implying a huge advantage in a range of applications. It took a bit more than a day of acquisition at 35 Kelvin, which is impossible without closed cycle system. We could see almost all expected cross peaks in DQSQ spectrum. Some of them are aliased because of the spectral lattice is limited by spinning rate, okay? The first thing we noticed this slight peak shift and broadening for phenylalanine here. So we wanted to more closely compare the exact peak locations in 1D data set. And this is looking at, the first FID taken from this 2D surface-only data shown in red compared with the regular CP in black. If you look at this blown up peak top here, it is pretty evident that peaks are shifting, especially the sidechain M and F here. They are closely packed in the crystal lattice, by the way. The peak shifts are sometimes slightly positive, slightly negative, and almost no peak shift over here. So it's clearly site-specific. In the beginning, I was like, is this real? But if I look at the conventional DQSQ, again, this is the first FID compared with the CP in black, almost no peak shift were observed at all, as it should be, right? So I conclude that this is real. The site-specific peak shifts are resulted from some kind of perturbation on the peptide conformation, might be related to some loosening of the crystal or the change in the crystal packing or crystal strain at the surface region, leading to a distinct time average of this fast, rapidly fluctuating chemical shift, as has been suggested in simulation work on MLF crystals. Although it is kind of difficult to quantitatively describe what kind of peptide conformation change has happened at the moment, because the change is a little too small. In applications, based on the ability to localize the radical molecule into the specific region in the sample system, we may try look at, for example, extended tip of amyloid fibers, the membrane raft associated biology, or polymer, modified polymer surfaces, which is a lot of time huge background signals from the base film. And with the site-specific delivery of the polarizing agent in cell, as has been recently demonstrated by Zander's group, we may be able to do some kind of organelle selective in-cell DNP, for which we are preparing methods and samples right now. So our system is pretty unique, and based on that, we measure the polarization distribution, as well as we do kind of hyperpolarized domain selective DNP, which may open up a range of applications in chemical, biological, and material sciences. So this is our team in Osaka, plus a lot of collaborators from University of Fukui for Gyrotron, Bridge 12 for the transmission lines, and Cryocura Cryovac. And on the NMR side, we have a very good collaboration with JOL. And of course, I want to thank all of you for your kind attention. Thank you.
All right, thank you very much, Yoh, for a very, very interesting talk, like showing us a closed helium cycle and then showing like low temperature MAS DNP is definitely something that is worth pursuing. If you're doing this in other countries where the electricity is cheaper. I don't know how much cheaper it is in America compared to Japan, and I don't know. But maybe just ask, let me ask a few questions, or one question and one comment before, so that the participants have time to type in their questions. So as we know, like depolarization is a severe effect, especially with MU-pol, and then some people have shown like the temperature dependence of it. So I'm just curious, when you do this at 30 Kelvin, do you measure the depolarization of MU-pol, and how bad is it? How much? Because you reported, I think, like 1,000 after taking a look.
Okay. Right. I think I have a data here on MLF. It's here you see this. This is combined depolarization effect plus quenching. You know, epsilon theta. It's very small for MLF.
Okay.
And for Yulia sample, like standard sample, we see it's getting worse, definitely, but it's not too bad. It's like a factor of 0.4,
okay,
0.35, something like that. It's kind of similar range.
Because people
qualitatively.
Because people reported about 50% loss at 100 Kelvin. So I'm just curious, at 30 Kelvin, you say you lost like...
Little worse, yeah.
Okay.
Not
and
crazy,
then like one comment, yeah. And then one comment is that when you show like the metal group, and then of course like Bob, you can comment on this. I think like the former grad student in our group, Cheng, like she has tried all this on bacterial dopsin. And she found, and then like we found that, I mean, deuterating like all these side chains, the metal groups, they actually improved the DNP. And not only that, and then like, and then not only that, it's interesting at low temperatures, some of the metal group, the three-side hot rotation, it will interfere with MAS, then your 13C peak will just disappear. And then if you cool to lower temperature, it comes back again because you are
actually it comes back, yes.
Yeah, exactly. Bob, you want to talk about it more?
Well, that's just slowing down the hopping rate to the point as you go to lower temperatures. A methyl group hopping rate isn't comparable to the decoupling field, the decoupling frequencies, and decoupling fails. Decoupling, and then when you go to lower temperatures, you go to the static regime, and then the lines come back. So that's an important effect, and it's particularly annoying around 80 to 100 Kelvin, where the hopping rates of many groups are comparable to our decoupling frequencies. Right?
Yeah, I think we seeing this coming back at 30 Kelvin. It's slowly coming back.
Yeah.
All right.
We studied carefully. Yeah.
Yep. So I'll just go to the first question on Q&A. So Aaron Rossini asked, for the double contact experiment, what's the definition of surface in your anti-phase filter? Does spin diffusion not lead to signal arising from a significant outer shell of each crystallite? I mean, so I think like if I interpret correctly, the surface like what is the thickness of the surface that you actually
measure? So the surface thickness is determined by the spin diffusion rate. So it's determined by everything. It's a parameter in your particular sample. In our sample, fully protonated MLF, we just assume the regular spin diffusion rate, which is a typical value. It's 1 square nanometer per millisec, which is observed for many protonated polymers and so on. We assume that based on this assumption, we calculated this will be 130, 140 nanometers from the crystal surface. So that's my definition of the surface of the crystal.
All right. Aaron, feel free to comment verbally if you like. I have unmuted you anyway. You want to say something, comment on it, because you have another question coming up as well.
No, I think that was good. Thank you.
Yeah, and then because you have another question when you're discussing, does the surface porosity match that the measure of the solvent enhancement and solvent polarization? Your glycerol peaks should be resolved to allow this.
The surface polarization match.
So you should be able to do your polarization measurement experiment on the glycerol.
Right.
And do you see the same level of polarization in the glycerol, the surface?
I guess let's take a look at, no, basically the glycerol was too small, because we wetting the crystalline MLF and thoroughly drain the glycerol matrix, not to too much disturb the further analysis. So it's kind of difficult to see it, I guess. But basically, in principle, it's possible to do.
Yeah, it might be interesting to do an experiment with labeled glycerol or something where you measure that.
Yeah, that's a good point. Because take a look at this. You see these slides, right? This is MLF. We're almost not seeing any glycerol peaks here in 60, 65. So yeah, let's think about it. Yes.
Yeah, and then a related question is that how do you make sure that some of your MLF crystals are not partially dissolved in a solvent? Or I think that's the question. Not to dissolve your crystals.
Well, it should be broadened out, right? If it is dissolved partially, and also MLF is it is known to very, very insoluble to water matrix. So I'm not worried about it.
Okay.
At this point.
Can I just make a comment there?
Yep, sure.
I think one thing you could do to really eliminate any dissolved fraction is you can use a T1 row or T2 prime filter, because usually if you have a dissolved molecule that's actually in the frozen solution, that's going to be fairly strongly coupled to the electron spins. So these types of tricks usually work well to suppress solvent signals, because those are strongly coupled to the electron spins. There's some pictures on that.
Okay, I remember I did direct polarization experiment, like directly exciting carbon and observe carbon under decoupling, and with short build-up delay. I really struggled to find this broadened peak in this experiment. I took like a crazy number of acquisition, and then finally we see broadened, PRE broadened carbon resonances. I guess from those experiments, the surface is pretty crystalline. Does it make sense to you?
Yeah, I think so. Thank you.
And then Dominic asks, the polarization build-up curve changes quite dramatically between 100 and 30 Kelvin. Is this because of the relative change in T1 of the matrix and material? Do you think like a VT build-up measurement could be useful for domain size determination or measurement?
Polarization build-up profile. Polarization build-up profile. So you're talking about urea sample, not MLF, the polarization buildup.
I allow
Is
him
it,
to talk. So
you're
Dominic,
talking about this polarization buildup?
Dominic, feel free to unmute yourself.
So I actually saw your paper on Chem Archive the other day, and you have MLF data.
Oh, okay.
Build-up times on the MLF samples. I was wondering. I think you didn't show it actually here, but
yeah, I didn't mention that. This must be it.
Oh yeah, that's the one.
Yeah. So it's very dramatic change we observe in of the build-up time. This is the enhancement factor as a function of the build-up time, right? It's very interesting feature we see in this. At high temperature, you get higher enhancement at shorter time. And if you go lower enhancement in the beginning. This is the plot in the semilog to look at this in the beginning part of the curve. The curve is really changing over temperature. I guess this is from change in the penetrations properties as a function of the temperature, because this is the build-up time as a function of temperature, right? At the high temperature, on is very fast building compared to off signal shown in black. And it's really changing if you go down with the temperature. And also we see almost single exponential at high temperature. If you go down, it's really multi-exponential, indicating that this is really the mixture of intrinsic T1 and the polarization penetration from the surface. So those changes will be reflected to those build-up characteristics, I guess.
Okay, due to time constraint, I will just take the last two questions. So I mean, you did not mention this, but perhaps in other talks, what's the advantage of using two gyrotrons? What are you planning to do? And then, do you have a sample exchange in your helium cool probe, or you have to warm it up all the way to change samples?
Okay. Sample exchange, we're working on that. It's coming up pretty soon because otherwise it's kind of difficult. It takes like 2 or 2.5 hours to change sample right now because we have to warm up and swap and put it back. And not too bad, but it's always better to have this exchange system. We're working on that. So two gyrotron, I didn't have time to say that. So one of the things, so many possibilities. We can do some kind of double gyrotron domain selection again. One of the things we could do is to, while building up the polarization, we could switch rapidly between the positive and negative DNP excitation rapidly here. And in between, we can accumulate the negative and positive polarization to the carbon polarization every time. And they do the observation. And then this will make this kind of polarization wave around the radical molecule, and it's diffuse. But over time, those diffusion is very diffusive, and it's going to cancel out over time, where it is diffusion, right? And exception is the space right next to the radical molecule, which is doing up and down, right, coherently, and we can chase it coherently. So it means that we can constructively add the polarization only around the radical molecule. So that's an idea. There is a validation experiment. It looks like it's successful. So we want to try some other biological things right now. So that's my plan.
All right, thank you. It sounds like another talk that you can give in our future Zoominar sessions when you have
Why not?
when you have the results. So thank you very much for your very interesting talk, and I will now pass the session to Bob to thank Yoh and also like to introduce our next speaker. Bob.
Okay, so Yoh, could you quit showing your slides, sharing your screen? Sorry.
Yes.
Okay, so the next speaker is David Bryce from the University of Ottawa. And David has a very interesting career. He did a solid state NMR PhD, and then went to ADVAX for a postdoc, and I presume did some solution NMR on proteins of various and sundry things. But then when he returned to Ottawa and took up his position in the chemistry department there, he reverted back to his origins, so to speak, studying quadrupole nuclei, and that's what he's going to tell us about today. So David, the virtual floor is yours. All right, screen.
Okay, there we go. So thank you, Bob, for the introduction, and thank you to Bob and Kong for inviting me to this Zoominar session. I guess in another world, we would have all been at Rocky Mountain Conference last week, so I think this is nice to have something to try to fill a bit of the gap in these strange times. And what I want to talk to you about